Flying a light aircraft between two smallish airports is one of the most difficult things you have to do early on in your career to becoming a pilot. It takes a lot of prior planning and preparation in order to not get lost en route and end up somewhere you don't want to be. So, how do we plan a nice little cross-country flight? Let's find out. Hi, I'm Grant and welcome to the fourth class in the flight planning series. Today we're going to be taking a look at a fictional flight between two small aerodromes in the UK while flying VFR. This will be basically a long worked example, slow and steady throughout the course of the video, hopefully showing you some of the things you need to consider when planning a cross-country flight in a small aircraft. Today we are going to plan a hypothetical route between two small airports in the UK. I've never flown this route before, so I don't know if it's a valid route that people do or anything, but that doesn't really matter because it's all about just showing you the theory behind how to plan this stuff. So our route is going to be from Carlisle Airport here, southbound, across the page and into a place called Barrow Airport. We're going to be using a hypothetical aircraft that makes the calculations nice and easy to understand. And later on in the series, we'll use the CAP 697 document to look at the single engine piston and multi-engine piston sample aircraft. Our hypothetical aircraft, the Vesna 172, has a cruise speed of 120 knots, meaning it will cover 2 nautical miles every minute. It has a cruise fuel burn of 12 US gallons per hour. The aircraft is not performance limited on either runway, and we are conducting a VFR flight, so we must be able to see the ground at all times and navigate using visual references. So the first thing we're going to do is get familiar with the airports that we're going to be using and the chart that we're going to be using as well. We're going to start off by looking at the AIP for Carlisle, or if you have had access to more friendly airport charts, then you could use them. We'll just take a little notes of anything that are important to our flight. So we can see by looking through that there are VFR operations allowed, which is good. The magnetic variation is 0.84 degrees west. They sell avgas, which is the fuel that most light aircraft use. Lots of information about obstacles nearby. The fact that it's an ATZ, which means we have a radio frequency to use when flying in or out of here. We can also see the circuit height and the ground charts. If we look back at the chart, we can also see that it has a little red circle around it. Then when we look at the key, we can see that this is an ATZ with the frequency we need written there, 123.605. We can also see various visual reporting points, VRPs, around about, which are good recognizable features that the air traffic controllers in the area will know the locations of, and it's a good reference for where we are. For example, if we look at this reference point down here, which is called Penrith, VRP Penrith, it's a town on a major road that runs roughly north to south. There's a very large body of water to its south and southwest even, with a river that runs north to south along it as well. So this might be a good feature to use on our flight to check we are going the correct way. And as we follow our route line down, we should be looking out for more distinct features. In this region there's lots of lakes, so they could be used as well as some of the mountains with spot heights and secluded little villages. The key is to select ones that will be easy to identify. And if we're ever sure on the symbols, we can just use the key. For example, this line here with this sort of, it looks like a dumbbell almost, this dumbbell line represents an altimeter setting region. If we didn't know what that was, we could look in the AIP and we can see here that it is a large area where they report QNH. So that when we set our altimeter, it is the lowest average for the region, which will make us fly at a safe altitude. And we'll have a look at safe altitudes next. After we figured out the information about our route using the charts and the AIP and all the clues available to us, we then go back to the AIP and look for Barrow Airport. On the AIP for Barrow Airport, we can see similar information to that of Carlisle regarding fueling, the lighting arrangements, the frequency, etc., as well as any restricted areas we need to avoid. It actually looks like it's owned by BAE Systems, and it doesn't accept visiting traffic unless arranged beforehand. So let's assume that we've arranged beforehand and they're happy to have us. So now we have an overview of our route. We know the airports will take us, we know we can use them, they have fuel for us, and we have all the frequencies noted down that we need. We've also noted down things that are significant to us, like the restricted area down near Barrow and the different altimeter setting regions which could come in useful. The next thing that is important is figuring out what altitude we're going to fly this route at. There's obviously some terrain en route, so we're going to have to make sure that we cover it. So the first thing we have to do is clear all those obstacles, and we do this by flying above something called the MSA, which is the minimum safe altitude. We find out our minimum safe altitude for whichever sector or whichever leg that we're on by finding the highest obstacle within 5 nautical miles either side of the route. Then we take the value of this spot height, round it up to the nearest 100 feet, and then we add on 1,000 feet with terrain that is 5,000 feet or lower, or we add on 2,000 feet if the terrain is 5,001 feet or more in altitude, in height. So for our route, we have roughly 2 sections. We've got the first bit down to Ambleside here, and then we have a turn down towards the coast and Barrow Airport here. So we need to create a 5 nautical mile or a 10 nautical mile corridor with the route centered in the middle and figure out what point is highest along that corridor. So if we take 10 nautical miles, which is what we're going to need, that's roughly 7.5 centimeters on this map. And if we use 7.5 centimeters on the ruler with 3.75 centimeters centered in the middle of this line, it can be quite difficult and it's easy to lose track. So what you can do is you can just make a little ruler. You've measured it on the scale and you can just run this up along the path and figure out the highest point on the route. So we're going to start off from Carlisle using our nice little ruler and find a spot height as we go down. So 5 nautical miles either side. We run down, we've got 804, 793. We can see this is the first one that we come to that's significant, 1799, a big tower. Or in brackets, it's 1192. And the brackets mean it's the height, and the figure outside of the brackets is an altitude. So that's the height above the ground and the height above sea level, basically. So you can assume that this terrain is about, 500 feet off the ground, and then they built a tower on top of it. So that's the first significant one we come to, and as we continue down our route, we start to come into a mountain range. So we can see 2306 is just inside. We've got 2808 down at the bottom here. You might not be able to see that. 2808 is just there at the bottom. As we continue down on this side, there's a point here which has 3116. And then we get to our turning point, still 3116 is the highest. And for our second leg, we've got 2635, which appears to be the highest on that leg. So for our first leg, it would be 3116. And for our next leg, it looks like this 2635 point here. You could have 2 separate MSAs for the different legs, but generally you want just one in case you're unsure of your position. You know that way you're above a safe altitude. So our MSA for the route is the highest obstacle within 5 nautical miles. We took that as the 3116 value. We're going to round it up to the nearest 100 feet. That's 3,200 feet. The obstacle is below 5,000 feet, so we just add on 1,000 feet for an MSA of 4,200 feet. So we know we need to fly above 4,200 feet at least. And when flying in VFR conditions, we fly at intervals of 1,000 feet, depending on the direction we're traveling, plus 500 feet. So we're offset by 500 feet. And what I mean by that is we fly at 4,500 feet, 6,500 feet, 8,500 feet, whereas IFR flights fly on the 1,000. So they're 4,000, 6,000, 8,000, etc., etc. This means that we're always separated from IFR traffic by 500 feet. And when we are above 3,000 feet in the UK, we normally fly according to flight levels. So we have our altimeter reference set at 1013, and now it references everything to a flight level. And it depends on which airport you're at, but that's a general rule for the UK. It might be different in the country that you are in. And the number of the flight level depends on the direction of our track. So from 0 to 179, we fly on odd levels. And then from 180 to 359, we fly on even. I know that technically all the levels are even because they end in 0, but hopefully you know what I mean. I mean 357 and 468, that kind of thing. So to find our track direction, we can simply measure the angle. So if we just get our protractor lined up, try and find a straight line, either vertical or horizontal, and you see there's, well, you might not be able to see because of the background, but there's sort of a grid behind, and you should be able to find a line that lines up with one of your grid lines, and then you can slide it up or down until you catch the track of your line that you've drawn on the graph. So that's looking to me like the first leg is 189 degrees. And for our second leg, it's looking like it's about 211 degrees. So 189 and then 211. So the first leg was 189 and second was 211. And that's our chart track according to true north. So we need to calculate the magnetic direction. And to do that, we use the variation, which is roughly 1 degree west in this area. On the chart, I'm not going to get it out because it's further out than can actually be caught on the screen. You can see a line of 0.5 degrees west and 1.5 degrees west, and our area is fully contained within those two lines. So to average out, we can say it's a 1 degree west variation. So to convert, we can use a very easy formula. CDMVT, so compass direction plus deviation equals magnetic plus variation equals true. If you don't know what that is, go and watch my GNAV video on direction, which I'll link below. So magnetic plus variation equals true. We've got the true, so we've got 189 plus the so magnetic minus 1 equals 189, so magnetic equals 190. So plus the variation with east being positive and west being negative. Sorry, I should have said that. So our first leg track is 190, and then looks like we're just adding 1 on. So it's 212 degrees magnetic for the second leg. You may be thinking, well, obviously they're both in the west sector because they're 189 and 211, but in some places, magnetic variation is quite significant. Could be like 20, 30 degrees, something like that, and that could swing you over the dividing line, and you have to be careful which flight level you're flying at because of this. It's important to note too that your country may use a different system for levels than this. This is just the one that works in the UK. A common one it being nose, which is north odd, south even. And if you're flying between two countries, you would obviously need to know the local rules and plan accordingly. So we've got that down, and we know that our two routes are flying in this west sector with a track of 190 degrees magnetics and 212. We're firmly within this section. So we want to fly at flight levels because we're above 3,000 feet in the UK, that's a rule. Our MSA was 4,200 feet. So our first available level would be for flight level 045. Cool, so we've got a nice altitude to fly this route at. But unfortunately, there's one more check we need to do regarding the temperature error. So basically, if it's cold, the different pressure levels get compressed down together. So our altimeter misreads. If it's cold, we're actually lower down than our pressure-based altimeter is reading. For more information, there's a video on GNAV, which I did on altimetry. I'll link that below. And it basically explains that what I've just said, but in a bit more detail. Everything's compressed together, so your altimeter thinks you're thinks you're higher than you are, sorry. So the error that comes about because of temperature is dependent on how cold it is, and if it's colder than a typical ISA day, we may be lower, and our true altitude will be lower than what it says on the altimeter. So to do an example for this flight, let's say it's the middle of winter, and the temperature is going to be about -5 degrees on the ground. So ground is -5 degrees, which means it's an ISA deviation of -20, because normal ISA temperature is 15 degrees, it's -5, that's -20 degree deviation. We use the coldest expected temperature on our route. That could be just in Barrow that it's -5, but in Carlisle it's -1. We always use the worst because that way we overcorrect and we're safer. And this is quite a common thing that you'll see in aviation. You sort of plan for the worst and hope for the best. So the error that we see in the altimeter is based off of this formula. We have got a 4-foot error per 1,000 feet per 1 degree ISA deviation. So for our planned flight level of 045, we have an error which is 4 times the 045 flight level, so let's call it 4.5 thousand feet, times an ISA deviation of -20. And that will give us an altitude, a temperature error of 360 feet. And it's so it's going to be -360 feet. We are 360 feet lower than 4,500 if this is the conditions. So our true altitude at flight level 045 is 4,500 minus 360, which is 4,140 feet, which is actually lower than our MSA. Remember, our MSA was 4,200 feet. So if we fly at flight level 045 in this temperature, the temperature error means our true altitude is below our MSA, which is really not good, because that way we might, probably wouldn't fly into a mountain, but we certainly don't want to be that close to mountains at all. So what we can do is basically add this temperature error onto our MSA. So we correct our MSA, and we have a temperature corrected MSA of 4,560 feet. So the 4,200 plus the 360, 4,560 feet, which means that our lowest available flight level on this route wouldn't be 4,500, because that's going to be below our MSA. It's actually going to be the next one up, which is not 5,500 feet or flight level 055, because that's in the east flying sector. We've still got to stay in the west flying sector. So our lowest altitude is going to be 6,500 feet or flight level 065. That way, when we're flying along, no matter what the temperature is, we're not going to bust below MSA, and that is going to keep us nice and safe. The MSA altitude is also based off of QNH as well, not a flight level. So if we were flying at a lower flight level, there might be an error between our flight level based from 1013, the standard pressure setting, and the altitude based off the local QNH, which again we would have to account for. So you've got MSAs, you've got to correct for the direction that you're going, pick a flight level based off that. Then you've got to think about temperature, and then you've got to think about the difference between altimeter setting QNH and standard setting if you're flying at flight levels. So just a little bit to think about. Okay, so that was quite a long step figuring out what altitude we're going to fly at. But let's assume that it's flight level 065. It's good for us with the temperature error, the local QNH to standard error is accounted for. We're significantly high above the MSA. that we need quite a difference between the QNH and standard setting of about 60 hectopascals to be even close, and that's ridiculous. So the next step is to plan a journey log. A journey log is a reference tool used to check your progress on a flight, with waypoints that we use to check fuel, times, levels that we need to be at, and any other important information that you need to help you navigate. The first thing we need to do is create some easy to spot waypoints near our route, and we then need to figure out how far into the route that is, what fuel we can expect to have burned by that point, how much time we can expect to have covered, etc, etc. So let's pick out some points first. And it might be quite hard to see this based off of what I'm pointing at, because this is obviously quite a busy chart and I don't want to be zooming in and zooming out the whole time, but I'll just talk about my process. So the first point we're going to use is this little point here, which is called Weatherall. It's a small town just outside of the control zone for Carlisle. So when we're in the zone for Carlisle, we might have to do some special maneuvers and follow a certain procedure to leave the control zone. So we need a point near the start of the route where we can officially get going. This is what Weatherall is going to be for us. And it should be easy enough to spot because it's on a north-south river, and there's a railway crossing east to west which forms a nice cross, and Weatherall is on that cross, and we know it's just to the south of the airfield. The next waypoint that we're going to use is this big tower here. It's a well-lit tower and it'll be just on the right-hand side of our aircraft as we're flying south. We will then use Ullswater Lake, which is the first big lake that we come to, and then we continue down onto the town of Ambleside, which is at the top of a north-south running lake, and it's a secluded little town in the mountains. Then we'll make a turn and fly overhead a forest until hitting the southern tip of another body of water, called Coniston Water, and then it's going to be a straight line on towards Barrow. We can just basically see the coast from here. There's a nice bay here, so I'm not bothering with another waypoint in between here, because we know if we just stay on the land with the bay just off to our right hand side, it's a straight line towards Barrow. Oh, I can't see that. So the bay there, and then Barrow is just in there. So those are going to be the little points on our table. We've got the departure, Weatherall to the tower, tower to the Ullswater, that first lake, Ullswater to Ambleside, the town on the top of the north-south lake, and then we turn, fly over the forest until getting to the next body of water, and then continue down towards Barrow. So that's our first point, and then we're just going to fill in the details. I've already pre-filled some of it just so I don't have to keep on going back to the map and measuring stuff. But for example, we're going to be using a generic aircraft. So we're going to use some basic figures for the climb fuel and time and the descent fuel and time. But if you had performance graphs, you could calculate these numbers more accurately. So let's say it's going to take us 10 minutes to depart the airport area and get ourselves to our first waypoint, which is Weatherall. And we're going to do that using 2 US gallons worth of fuel, and it's going to be the same for descent. These are just generic figures. We'd be a little bit different in real life. So that's our departure. We've got to Weatherall, and then we are going to try and fly from our first waypoint of Weatherall to the tower. We know that the track is 190 degrees, and we'd have to turn to an appropriate heading to achieve that track. And we'd calculate that heading using something like a CRP5 computer or another similar flight computer that you might have. For our example today, we're going to use a steady wind of 180 degrees at 30 knots. And this will influence our heading and our ground speed, which will influence our time and our fuel burn. So the way to do this is you pop a wind at the top. It's a magnetic wind of 180 and it's a strength of 30 knots. So we're going to go down to this little cross, put on a cross at 30, and then we slide up to our cruising speed, which is 120 knots. We've got up to our cruising speed. and then we turn it to our track, which is a magnetic track of 190 degrees. And then that has a drift on it of about 3 degrees. About 2 degrees. So if we turn to 188 degrees, that would mean we're correcting for the drift. So our magnetic heading might be 188 degrees for this first leg. And we can see a ground speed of about 90 knots. And that should apply until we get to our turning point. So we've got 188, 188 for this, and a ground speed of 90 knots. I've not actually left a space for that, but I'll write that down on the side and we can figure out a time. And then for the next leg of our journey, we just basically have the same cruise speed, same wind, but our track is 212, which is about there. That's a drift of about, what's that, maybe 8 degrees. So if I turn 8 degrees into the wind, that's going to be 1, 2, 3, and then there. For an estimated heading of about 204 degrees. So we'll take 204 degrees and 204 degrees all the way to Barrow. And that makes a ground speed of about 95 knots. Let's make it for easy calculations. Then we would measure the distances from our point to point. And a good way to do this is to either use a ruler or you can get a set of compasses. Just put the distance between the two, go down to the scale and see what the distance is. So this is the rough distances I've measured earlier, 9, 10, 8.5, 8. And that's fairly good spacing for a route like this. It means you have a consistent checking. You have consistent checking through consistent waypoints throughout the route. They're all round about 10 nautical miles apart. So it means that you've got a good interval to be checking. You wouldn't want 3 within the first 10 minutes and then half an hour and then check another route, because you can drift a lot in half an hour. Whereas if they're every few minutes, you can make corrections if you need to often, and you do little and often rather than a big one that sends you way off route, for example. So we would then calculate our times that it's going to take. So for this first one, it's 9 nautical miles. It's going to be divided by our ground speed, which was 90 knots for the first one. So 9 nautical miles at 90 nautical miles per hour is going to be 0.1, and that's in hours. What you can do is you can press this button here, which is like a dot, a comma, and then 2 commas, and that converts it into hours, minutes, and seconds. So you can just do, that's going to be 6 minutes. The next one, the next leg is 10 nautical miles at 90 knots. Again, so that's going to be 0640. And then you can just keep doing this for the whole thing and you get a list of times. So then you have your list of times, and then you use the fuel burn, which was 12 US gallons per hour, to figure out how much fuel you're going to burn en route in terms of US gallons, and you might need to convert to litres, depending if your aircraft has a fuel measuring in litres or gallons or something like that. So let's do that. So now we have estimated times and fuel burns, an estimated heading and track and distance, MSAs, all the information that we might need in order to safely conduct a flight. You also might see secondary columns in journey logs to actually track your progress. So say we realize our heading on the first one of 188 was making us drift to the right, we might correct it because we are over correcting for the wind, for example, and just make our magnetic heading 187 or 186, and that was actually sufficient to fly the designated track that we wanted of 190. Just things like this. This is just a rough plan, and it can be adjusted as you are in the air, as you see fit. To help you to help you fly the plane on the route that you want at safe altitudes, tracking your times and your fuel burns, making sure that you're burning the correct amount of fuel, not losing fuel, things like that. So this is just a nice tool to start off your day with, a fully completed journey log.